Hi, I'm Will Forman. I've been asked to say a few words about my history in deep submersible construction and design and operations. During World War II, I served 4 years in the Navy as a dive bomber pilot on 4 different aircraft carriers. I got out of the Navy after the end of the war and went back to school to finish my engineering degree. My first job after school was as an engineer in a job shop where construction and with welding and machining and that sort of thing was part of the daily routine. During my Naval Reserve time as a weekend warrior, I had a 2-week assignment to the Naval Ordnance Test Station in China Lake in the middle of the Mojave Desert in California. Towards the end of the first week, it became apparent that a lot of varsity type defense work was going on, and it was an interesting place. And at that time, which was January of 1960, the same month that Trieste made the deep dive, at that time the director sent around a memo indicating he would be interested in someone designing and constructing a deep submersible for 2 men that would hover like a helicopter and be able to pick up torpedoes off of the San Clemente Island test range near Los Angeles. It interested me, and I spent a lot of time at the library, which they had a beautiful, complete library system. And there I looked up all of the different submersibles that existed at that time, which were very few, to see if I could get some idea of what was entailed in the design of a deep submersible. The Trieste people were nearby in San Diego, and I contacted them, and they seemed quite ready to help with the design and the idea. Since they had such a large submersible, they were interested in also having a smaller one for smaller jobs. They were particularly helpful in operational procedures and details. A number of other places were referenced in the library. The works of Beebe and Barton during the 30s, although pretty ancient, some of the environmental systems were still pretty much similar. And so their work was interesting and useful. The Japanese had their submersible, but it was on a tether, so that kind of eliminated some of the usefulness of their stuff for me. The French had the most useful submersible called diving saucer or soucoupe, and it was a two-person submersible for 1,000 feet with water jets for propulsion on the outboard equator of the pressure hull that would would pivot to give vertical thrust and remain horizontal for forward. So I came up with my own design suitable for what was available on the market and within my skills in engineering. The idea of a spherical hull was primary, since it was the most efficient strength-wise geometry. The Deep Jeep, which we named it, was to have a spherical hull with batteries below it that are droppable and propulsion motors, electric propulsion motors outboard at the equator of the sphere, and a viewport at about 45 degrees from the bottom up for where the viewport was located. Of the finite parts like how to drop the batteries and how to get buoyancy at the surface, some of that detail was browsed over, but I did make a proposal, and by using boiler steel for the pressure, two pressure hemispheres welded to a sphere, by using that sort of technique, I could get the cost of the hull at a minimum, and it could still have a strength comparable to the steel, just almost comparable to the steel of a World War II submarine. So I turned that proposal with a lot of the details of how it would operate into the director's office, and to my surprise it was accepted and funded for construction. The pressure hull was obtained from Lucan Steel. It was advertised as any end closure to a boiler tank could be made available and delivered in a week. So I made the specifications of 5-foot diameter and ordered two hemispheres of 3/4 inch A27 boiler steel, and I was quite concerned about the out-of-roundness and general sphericity. The environmental system had a number of possible places to get data. I chose the station hospital, which was run by the Navy, and they let me have the information on oxygen required for 2 people, and carbon dioxide scrubbing techniques, which was soda lime in this case, and the indications of both the feed rate and the existing content of the capsule of both oxygen and CO2, to have a percentage readout to keep it, and the approximate variations that are permitted and still be healthy. The Dr. George Bond showed up to our surprise one day. He later became Captain George Bond and was in charge of the Sea Lab project, which some 15 or 20 men spent a month at several hundred feet in the ocean. But at this time he was still commander, and we showed him all of our information we had recorded from our tests that we'd made while we encapsulated in the sphere with the hatch closed, and spent 4 to 8 hours inside using all our equipment and keeping proper limits on excess or minimum limits, and they were pretty good. They were pretty good readouts, and Bond seemed to find them agreeable, but he had a gloomy look at the whole time he was there. And our safety officer from the base was with him, and they were both submarine trained, even though he was a doctor, and they kept looking at each other like some kind of disbelief. But the next morning, after they had reviewed everything and gone out and looked at the equipment, they were surprised to themselves and happy to relate that the system was completely successful and useful, and they would pass it, but that they didn't think anybody could make a complete system for under $500. Our competition on the base was another undersea vehicle, and they were in the thousands for their systems that were expensive laboratory systems. The lead acid batteries were deep cycle go-kart batteries, and they were located in the bottom of the pod beneath the sphere, which we made droppable so that we could have two sets, one in use and one being charged at all times at sea. The screw that held the pod on was a heavy bolt with square threads that was capable of the 1,000 pounds of batteries that we had there. The propulsion system was little half horsepower electric motors driving 12-inch propellers and in pods located on the equatorial line of the pressure hull. We had a unit for a pod on each side. The propulsion pods rotated about the axis between the two of them that let them tilt up or down, and for horizontal excursion, why we would keep them level with the horizon. This was similar to the soucoupe used with jets, and was quite efficient considering we at a half horsepower we were getting 2 knots. Our wet diving or real diving started in the quench tank of the welding shop, about a 10-foot tank and some 20-foot deep. After we cleaned up the water, we encapsulated for the first time. There's not very many tanks available in the middle of the Mojave Desert, and that was our first one that we tried, and it was very educational and useful. And the next time we had the entire sub together, we went to one of the swimming pools and operated there just enough to get used to the handling. I got a contract with the General Motors Research Lab in Santa Barbara for the use of the Swan, a retired Navy wood boat for use around for anti-mine protection, and it was the same ship in build as Cousteau's used on the Calypso. So General Motors provided us with our early times in the ocean, and it was quite an experience. We went to San Clemente Island to the naval base there with all the equipment for handling off the dock at Beavers Point, and we went from the Swan at General Motors to the YFU 53, which was a LST that was converted with a center hole with an elevator that was lowered to as much as 1,000 feet. And we worked from there and made our deepest dive to 2,015 feet, which proved pretty much that our 3,000 foot pressure tank, 3,000 foot of pressure in a tank that we had tested the hull, it gave us a 50% safety factor for the 2,000 foot operating depth. So we were happy and considered our services finished when we got word that the aircraft, the B-52, and the tanker blew up over Cartagena, Spain, and 2 of the hydrogen bombs had been released in the explosion and had floated down in their parachutes, one on land and one in the water near about a mile from shore. And we were volunteered to go help look for that. and hopefully lead to its recovery of the one in the water. The Alvin was in complete overhaul at the time and was spread all over an aircraft hangar at Woods Hole and was unavailable. So our work was to do what we could until they could get there if we didn't find it.
Deep Jeep is a two-man research vehicle capable of depths to 2,000 feet. Basically, it is a 5-foot steel sphere with a battery pack at its bottom and a syntactic foam float at its top. Weights held on by electromagnets encircle the bottom of the vehicle and are used for ballast variation. The chemicals used in Deep Jeep's air purification system provide the vehicle an operating time of 4 to 6 hours and up to 60 hours in an emergency. Unlike the Sucoup, whose passengers recline, the Deep Jeep operators sit upright. Deep Jeep is designed as a work and research vehicle. Its potential uses include performance of manned work in deep water, geological and topographical surveys of the sea floor, and investigations of ocean phenomena such as the deep scattering layer, which acts as a false bottom for sonar signals.
Heave around. Hill, towards the power drive.
Having watched the launch of Deep Jeep from the deck of the YFU-53, observers returned to the instrumentation room to monitor the submersible's maneuvers about the submerged frame. In this dive, Deep Jeep was to move several hundred yards away from the control vessel, then locate and home in on an acoustic pinger mounted on the frame. Communication with the surface ship is achieved with an ultrasonic telephone system which provides reliable communication at distances up to 2,000 yards. Two motors, located one on each side of the vehicle, can pivot simultaneously or separately about the vehicle's lateral axis. The submersible is maneuvered by altering the speed of these motors and the angle of each propeller. In fact, Deep Jeep's flight through liquid space is much like that of a helicopter.
Affirmative, topside. This is Deep Jeep. We see the frame just below us. Moving in now. Can you see us? Over.
Roger, Deep Jeep. I have you in sight. About 250 degrees from me, approximately.
Despite the fact the control systems of both the Sucoup and Deep Jeep are considered to be somewhat primitive, the vehicles were found to be capable of the hovering and settling maneuvers required for submarine rescue work and for deep recovery operations. Ideally, man would like to do on the seafloor what he does on land, tarry in some selected locale, or move rapidly to some distant area of interest. Submersibles like Deep Jeep and Sucoup will enable man to familiarize himself with a particular area
In June of 1965, the owner and manager of Sea Life Park in Hawaii visited China Lake, where we were operating and living. I had a model in a tank that was remote controllable of a little hot rod, I called it, which was an acrylic sphere. It was about a 6-inch model. An acrylic sphere with the entire Deep Jeep propulsion system on it, with rotating electric motors. In this case, they were slot car motors from my son's collection, and had little pods underneath the sphere that took the place of batteries, and we would run it around in this tank, and it was a regular little hot rod. It would go in and out of pipes and caves and stuff that in our mock-up tank, and it was a kick. And the owner and manager of the Sea Life Park got one look at that, and I couldn't get him off of the controls and running the model. He said, "I got to have one of those. I got to have one of those for my research lab. I got to have that." And I said, "Well, money, marbles, or chalk, you know." And he says, "Oh, I'll fund it. I'll fund it. Business is good. We can. If you don't need it all at once." I said, "No, I need the money for the sphere is the biggest deal." And he says, "Well, get it. Get the sphere." And I said, "Okay." So I located a fellow named Forman up in Saugus, California, that was a acrylic fabricator, and he was fascinated by the idea of what I was doing. I had some demonstrations on video, and it was pretty impressive. And he said he would try to make one, but he'd have to make it out of plate acrylic, because at that time the casting of acrylic had not developed yet. And this took a while, and I'm sure there was some bad words spoken, but he stayed at it and got it, and they used the glues of the day that were quite good on acrylic, and we ended up with a sphere, and I took it to Hawaii, or had it taken to Hawaii, and we got the only vertical lathe in all of the islands there to carve us a hatch hole, and I reinforced the hatch hole like you do where you have that sort of thing interfering with the main structure. And so we had our sphere, and along the way, we had to have the production and construction done in Hawaii, because I was doing this in my spare time, and I was spending every weekend for 2.5 years in Hawaii working. Well, everybody envied me going to Hawaii, but all I saw was United Airlines Flight 104 going out and Flight 105 coming back on Sunday. But it worked pretty good, and we practically wore out the telephones, and I sent them all kinds of drawings. This was before email, so the drawings had to go by snail mail, and that was just handicaps of the day. So we tested it. The motors and the batteries and all were quite familiar from the other sub. We tested the entire unit to 500 feet, and we had some automatic strain gauge readouts that when we brought them back, the structural structure was quite adequate for a lot more than 500 feet, and probably for 1,000. So we were happy with that, and we were delighted to take people out in it. It was the only time I ever saw somebody get excited while they were diving as much as they did. We were off of the point, Makapu'u Point, and there was a few sharks around, and one of them came over to look at us, and he went underneath, and we both lifted our feet up so the shark couldn't get us, and looked at each other kind of stupidly afterwards, because obviously he couldn't get inside, but just the natural instinct to get out of the way. So we had some good dives, but we needed a launch and recovery system, which on the little island of Oahu, there was not any great sized ships available, and if they were, they couldn't have afforded them. So I made the comment when we were doing a brainstorm after a day's work there, I made the comment, what we need is a wet aircraft carrier. And that after a few ugly glances from the people around, I said, well, at 100 feet, you have practically zero disturbance when you have a 4-foot waves at the surface. And it's an oceanographic principle that the wave circles, the circular motion in the wave depletes by the exponentially as it goes linearly to depth, so that if we wanted to go to 100 feet for pickup, because the water's never very calm around here, we could land real cool, and divers could help us get into the catches and secured, and we could bring it back to the surface and drag it over to port where we had a crane. So one of the guys said, well, we've got an old catamaran that's not doing anything. It's a little small, but it would work. Why don't we work on that? So that's what happened. And it took a bit of jockeying with, but it worked marvelously. And the picture of the Kumu aboard by the way, the name became Kumu. The full name in Hawaiian is Kumu Kahi, meaning first in a series. But we landed the Kumu on the launch recovery transport catamaran at 100 feet, and it just was like a dream. It was the smoothest recovery and launch that I'd ever been in. And all we did was put a small tug on the thing to bring it out to the dive site or to bring it back from the dive site. But you had to have divers in the water, jockeying the air tanks. With depth, they changed buoyancy and so forth, but that was soon handleable. And the University of Hawaii was in possession of the Pisces 4 and 5 for, I don't know, 15 or 20 years, and they fell in love with the system, and they made their own LRT to our design, and they used it for 10 or 15 years that I know of, and they were still using it when last I saw them. And Kumu was a total success, and the LRT outlived the submersible. In December of 1965, the director called a meeting of a large group of us, and most of the people had been getting information on who would construct a glass sphere that was 56 inches in diameter to be used as a pressure hull. The groups in different ones assigned to different countries had looked all over the world and done a terrific job, but they could not find but two possible sources. First off was a man in Washington State, and he had said that he would take a contract for something like $1 million, but it would have to be a best effort contract, which means he could hand you a wheelbarrow full of broken glass and it would still have to pay him for it because he had done his best. And the purchasing agents in the area at that place in Los Angeles would go into a panic mode if they ever saw best effort, because it was just considered to be a ripoff. The other possible source was Corning Glass, and they said they thought maybe the first one that one item, which would be the first one, would run over $1 million, but they weren't sure. And I commented to the director that on my limited experience, we would need 4 or 5 of the things because they got broken one way or another. And so that pretty much put the gloom on that possibility after quite a lot of effort. And one of my helpers had indicated that he thought Corning had some already made, some hemispheres already made, but they weren't very big. And so I looked into that, and they were 44 inches in diameter. And the director by then had discharged the group and held me back and said, "Is there any way you can use 44 inches?" And I said, well, on the spot I was kind of stuck for a snap answer, but I said, well, you can always put it on the end of a steel cylinder and have the people lay down inside. And he said, why don't you do that? Which gave me $150,000 a year for 3 years. And so that's what we attempted to do. And I immediately went back to Corning to confirm whether my information was solid or not. And sure enough, they had a surplus of these hemispheres of glass, about 2 inches thick, and they'd been used when they were glued together to make a sphere, hemispheres glued together to make a sphere, and they were used as buoyancy pods to hold up the transatlantic cable that was being put in new in fiber optics, and they prevented the line from going down deep chasms and coming back up and wasting a lot of line, so they could buoy it more or less parallel to the surface this way. And so I haggled a little bit about cost, which I had never haggled over $10,000 items before, and that was the price we ended up with after they had thought of adding a little bit to it when they heard that we had some use for them and they had none. So we were in the business of a glass being the major portion of a pressure hull of a deep submersible. And I didn't think it would be much of a problem with glass. It was, and it took several years to figure out the weaknesses and the strengths of glass. Basically, the material in its pure form is good for as much as 200,000 psi in compression, which compares with an exceptionally good piece of steel. However, the glass in general, and it pretty much holds for all alloys of it, has practically no tensile strength, and thus the term brittle. You drop a piece of glass and it breaks, and if you break a plate glass window, it breaks into many smithereens of pieces and parts. And the technique for commercial glass is to quench the material while it's still hot, but able to be handled, and that puts the surface, it treats the surface so that the entire piece is in compression, and until you exceed that compression with a scratch or a hammer, it takes a lot of bending, and it has a superfluous additional tensile resistance. It doesn't, so the problem then was to design the steel hull, which was fairly standard submarine ring stiffened cylinder technique, and we did that, and we had a large set, and it ended up about 12 feet in length, and we had 2 battery pods which served as of course containers for the batteries, as well as landing booms to set upon, and it was 1,100 pounds of droppable weight and it would have to be a fairly serious emergency before you drop them, because you would lose your stability and roll on the way up if you drop that much weight. And in tests that we made during christening or following christening, we actually, in about 50 feet of water, dropped the batteries, and indeed we did roll 3 or 4 times before we got to the surface, and discovered all of the dirt and missing files and tools that we had lost. We were wearing on the way up as it revolved. But we were able to use the technique. We made dives at San Clemente Island. We did make dives at San Clemente Island in our first go around, and then we went to Catalina, and at the Isthmus is a marine railway that was left over from another project, and we found that tremendously useful, because you can drive it from up on a hill into 20 feet of water on a railroad track, and then get off or on your submersible. A little like getting back to my old way of landing on shipboard aircraft carriers. Stop. We started working on the glass to see how much stress we could put on it, how deep we could go, and how we would fabricate it, because trying to machine a 44-inch hemisphere of glass on a normal vertical lathe is a pretty good trick that you don't run across every day in a shop. So we started with 10-inch Pyrex, by the way, is the alloy, which is a common kitchen alloy of glass, used because it doesn't expand or contract significantly under changes in temperature. And sudden changes in temperature for some glass will break it, particularly if done quickly. So we started with 10-inch model, and we copied a lot of techniques used in the laboratories for glassware. A lot of plumbing and filters and mixers and stuff are used by the chemical industry and study groups. And we could put the glass hemispheres with flat edges against steel plates and put some neoprene to soften the contact. And we could get up to some pretty high pressures, like 10,000 feet equivalent in pressure. This was encouraging, and we tried different metals, and we had pretty good success, and we tried different gaskets, and we got better results with reinforced gaskets. So we went to a full scale, a 44-inch hemisphere, and took it to Southwest Research in Texas and tested it and blew it, imploded it. We put the glass with the rounded part toward the floor and the open part onto the steel toward the ceiling, and we made a regular shape charge that blew a hole in a corrugated roof of the test lab, and had pieces of glass no bigger than an inch cube, and a lot of dust like Portland cement dust. And they certainly found out that big glass isn't like little glass. And this was our first shock of many to follow. So we decided quite quickly to go into a system where polarized light is shined through samples of the glass under pressure, which means you have to take a segment of your in this case pressure hull, and put it under pressure in a pressure gauge system, and look through lenses. And if you know the system, you can actually look at the rainbows and count the numbers of complete rainbows and get a actual stress reading. And it's a well-known technique in the glass business, but was new to us, and it's terribly useful. You could use it on acrylics as well as on glass, as long as it's transparent. So we worked on the flat edge and could see why it was just horrible under polarized light. It just looked like it was already cracked even at the low pressure that we put it under. So we tried different edge configurations, and long story short, we found that a rounded edge kept the surface in compression and without any sections of tension, and that a little bit longer radius was better than a half circle, and that we also found that the material that it was pressed against made a difference, in that steel would pull the glass apart physically, regardless, partly due to the pressure, but partly due to the fact that the steel moved sideways faster than the glass did, and it pulled it apart. And so we learned that lesson. And so in the end, we had a rounded edge, and we found we had to use a ring of titanium, which had a more closely related physical properties to the glass than the steel did. And then the ring of titanium was up against the steel hull. And this was our final design, and we took the entire configuration of the pressure hull to a depth equivalent to a mile deep in the ocean. We took that in a test chamber, and we repeated the cycling, and we found no problems after several hundred cycles. It didn't seem to be cycle weak. And so we actually got a certification from the Navy for a glass submarine, which I didn't think we'd ever get. But they limited it to 100 feet, and with the idea that after we made some dives at 100, they could increase the depth, but they wanted to see how it worked out in handling and operation in general before they gave it a deeper certification. So the Deep View ended up in Hawaii with the porpoise research people, where they were training the porpoise for military purposes and trying to watch what they were doing as they moved along, because we had pretty good power. We had 5 horsepowers in each motor for horizontal propulsion, compared to the half horsepower we had in Deep Jeep. So they were happy to have 5 or 6 knots, even though the porpoise could do much more than that. But they spent over a year with the Deep View in Hawaii with the porpoise.
Yep.
In June of 1966, I was having my usual get-together with the pilots from Trieste, where we about once a month would get together for discussions on what was happening in the business and who we knew got married and this sort of stuff. And one of the fellows was Larry Shoemaker, who I became lifetime friends with we kind of paired off because he had an idea that he kept trying to bring up in our group discussions. And finally, I paid attention and said, what do you want to do? And he said, well, we should get all the pilots together in one group from all over the country and meet from time to time and talk about our operations and what went right and what went wrong, and we should regulate who can be a deep submersible pilot and have rules for them to meet and attain, and we should do something before the Coast Guard or somebody else starts regulating who can drive these things and who can't and so forth. And he said, we ought to do it ourselves. And I said, well, that's not a bad idea. Only thing I don't like about it is that I didn't think of it. I'll help you. And he says, oh, and he lit up and he was pretty happy about getting started on it. And he rattled on about some of the details for the better part of an hour. And I was at that time at China Lake, and he was in San Diego, and we would talk by phone, but we got so we would meet on Sundays in Riverside, halfway between the two of us. We'd take our families and have a picnic, and when everybody was happy eating and all, we'd get to decide, and we'd talk about our new Deep Submersible Pilots Association. And it got pretty serious and pretty intense, and we started calling around to other pilots. There weren't so many in those days. We talked to them. We got finally ended up that we had a meeting in Houston in January of '67. And we had 16 people from all around the country that were our charter members, and everybody had done their homework on what we needed to do and what we thought we ought to do and not do and so on. And so we spent 3 days there with some help from a couple of the astronauts on how to write our Constitution, because they had a group, and one of the men from the Experimental Pilots Association stayed with us all through our time of gathering the Constitution together, and we even elected officers in the corporation and formed a corporation registered in California, non-profit. And we had president and treasurer and secretary and so forth, and membership chairman. And we decided to have monthly meetings in San Diego. And we met at one of the restaurants that was receptive to our meetings with, and had a room and for show and tell. And for 48 years, we had get-togethers where we really swapped information, and when nothing was hidden, and it was all, some of it was proprietary to the organization, so that we didn't violate any proprietary rules, but we wanted to know who almost got hurt or so forth. And in the end, 48 years later, we never had a serious accident, nobody was killed, and we had thousands and thousands of dives that were satisfactory. And we closed off on a January of 2015, exactly 48 years from the beginning. Another goal, need for our availability. It should be, and we will try to be, as available, both the vehicle and the pilot, for customers in the science or military as we are needed, in line with any suitability and funding that they have. Period. One of the things that Larry had worked on was a guide for the selection and training of deep submersible pilots, and it was a very effective tool. In conclusion, some of the highlights that occurred over the 48 years of the DSPA existence are worthy of mentioning, though there are many more. A total of 250 men and women were pilots of DSPA for the full, at one time or another during the full 48 period. At their use was over 60 submersibles from 8 countries of different manufacturers. And although there were thousands of dies and of different kinds that are far too many to list, some of them were critical to the country and in some cases to the world. In one instance, the hydrogen bomb that was lost off of Spain was a very delicate diplomatic problem for the country, and several of us in our submersibles went to the scene and made efforts to retrieve it, which the Alvin vehicle finally did spot it and recovered it and saved a great deal of politicking for our government. The 2 nuclear submarines that crashed and went to the bottom had exposed C4 of their crashed products, and these bottom scenes were of critical importance, both for human reasons, political reasons, and for scientific reasons. Bottom of the ocean, thermal water exits were discovered by Shoemaker on one of his dives, and were astounding to the science people in that the water was hot enough to melt the viewports on the submersible, yet there was bountiful amounts of life surrounding the outlets, where it was in the proper locations was warm enough for adequate life and a lot of nutrients from the minerals and foodstuffs in the water. To this day, they still argue whether that might have been the beginning of life on Earth by coming in from space and cooling and falling to the bottom with the right amount of nutrients inside for life. After over 50 years in the deep submergence business, designing, building, and piloting 3 deep submersibles and operating 2 ROVs, I consider the time well spent and enjoyable with all its ups and downs. And I envy people in the business nowadays with all the new things that are coming up. But we started enough things like discovering the deep thermal vents, and some of the medical materials that we had our share of discoveries, and they were fun. I look forward to the new deep submersibles as they are built and piloted, and I envy the new technologies, and I look forward to the new safety systems that must evolve internationally, rather than each country having their own set of rules. When we're operating these submersibles all over the world, and that we'll have to remain to see, and I wish all in the business the best of luck and good diving. Thank you.